Yes, I got it.
When we talked about like the lower limit topology where you can create some things that used to be discontinuous as continuous.
Yes.
It's kind of an application question with physics, so I don't know if it's totally makes sense to you, but we're talking about like conductors and like how the electric field is discontinuous at like the this surface. And my teacher, I try to say like, well, it could be continuous, right? If you choose the topology. I jokingly say this at the end of class, like, say, I was like,
How many hours did you get?
Send the kernel all over. Yeah, I did.
Oh my God.
But he asked a good question, like, when would the application be, I guess, useful? Kind of like, would there be ever a situation where you could make something that used to be discontinuous, continues in a different topology? Would that be helpful? That's what I wanted to know.
Yeah, I think when you're doing an application, you want to do the right topology. You want to be able to choose the right topology. So I actually said something at the meeting, like I'm really good at air chalk. So I did some air chalk stuff, but I think one day we could look at the microbiome. So what they do is microbiome specialists, they take poop and then they sequence from the stool you get raw sequences. And what they're doing next is they're trying to map the sequences. Like it's just overwhelming amounts of sequence data. And then they take that sequence data and they map it to species. And they can't come up with what's called these operational taxonomic units. So it's this table where you have one person and you have counts of a lot of species that they have. So everything's now integers. And what happened is that they were using, like if I wanted to say, look, how are you and I different? I need to somehow calculate the distance between you and I. And so they're taking these integers and then comparing them with Euclidean. And that's messed up, right? That doesn't make any sense. And so recognizing that you can't use a Euclidean distance, they came up with something that is, they call it dissimilarity index, which some people call distance still. And I went and looked at it and went, not a metric. Like I just checked it and like, not a metric. Then Colonel Crow took that metric that they have, it's not a metric, and he was trying to visualize it. And he said, I did PCA and it worked and it looked like something, but when I did this and I put it up there, it didn't look like anything. It's because it's not a topology. That's why. And so really what you need is to change the topology. And so we're going to look at some today that have integers. So you want to use the integer topology, right? You use a distance that makes sense.
Yes.
And that's the most annoying thing a mathematician can say. You're not in the right topology. Like oh, don't invite this person to the party. Note. It's right. That's why they're not able to visualize something. And it strikes me that there are a group of mathematicians studying this area, but the vast majority are using something that's not a topology. So you can see things, but you can't, it doesn't really make sense once it's in this other space. Okay, so today is.
He's actually. Sir. He shows that for those games. Yes.
Try to stay simple.
It's a lecture given trouble. No. E301.
Oh, yeah, that's what I'm saying.
What's the other class?
We have electrical.
I heard somebody else, you're the only one passing that class, right? That's true. Or you used 301? Yeah.
Oh,
You're
no.
gonna be taking exceed 303.
You're the only.
You're gonna hate that one more.
Yeah, the mids are not too.
Yeah. Yes, I need the class structure.
I need classes, but in particular, electrical.
Expect you to do 80. And then assess your homework.
But you, like, it's gonna be. I'm literally trying to go. I don't have to speak for it, like, it's.
And then you have this, which
That
was
is
open
just
space.
so me when I try to enter it.
No, it's
I
open them, articulate. It's like, see, what, see, the difference.
So I'm skipping parts of this. There's the product topology, which makes complete sense, the way it should. So I'm skipping that part. Let's see.
What,
Oh.
is that a button type of thing?
What'd you say?
Is that just like a, I believe button type thing?
Okay.
The product topology is when you cross, like take two topologies and you use the ordered pair.
Oh.
It's almost like what you think it should be.
I want to see, how it's different from the box topology.
Is,
Like, I know how
Yeah, but. All right, we'll do product topologies, but it's a little bit more of what you think it should be.
is cross and is the cross product.
Okay, so this is all from chapter 3. We actually have gone ahead to chapter 4, but here's where we come up with the Mobius strip. All the figures, the Klein bottle, all of that is in this chapter for introduction. So I went back, they have talked about it in the other chapter, I think it was chapter 4, that I started in on. I'm like, oh, we need to go back to chapter 3 so I can introduce these special topologies like the Klein bottle and the Mobius strip. So let me first start with what if you have, so in math, we have a subset and it isn't what we want it to be. Subspaces are exactly that. So if you take a subset of vectors, it's not a subspace because I can add out of it and I can multiply by a scalar and get out of it. So you ask yourself, well, what do I have to do to that to make it a subspace? You get span. So we do this all the time. You know, if you have a subset that's not a sigma algebra, how do you make it a sigma algebra? So this happens and it's embedded in something that is a sigma algebra. Same thing here. Suppose I have a subset. Subset Y of a topological space X and I define a collection of sets that's my U's look like upside down union. I mean, it looks like a union, so sorry for that. Maybe I'll put like something on it. I don't know. Maybe I'll do this. So you put a tail on it. So I take this set Y and then I take U's and intersect them with Y. This collection of sets, or this set TY, is a topology. And the open sets are going to be these guys. So not to be confused with subspace from linear algebra. So I'm going to put the word topology here. Colin Adams doesn't. But just to remind you, it's not subspace from vector spaces. It's subspace topology of X. All right, I'm going to have you take boards and play around with one, okay? I'll wait till you guys are done copying this.
You, highlighted why to be open sets, are there certain,
Those are the open sets.
okay, all open sets? Where,
The one, you take the open sets from the big topology, intersect them with Y, and they're the open sets in this new topology. Right? So I'm going to have you play with this.
oh, so why?
So try this out. So example. I didn't have a printer on the plane, so all our board work would just take pictures and send them to me today. take I equals the open and the closed interval I 0, 1. That's contained in R with the Euclidean topology. So R is equipped with the Euclidean topology. What are the open sets in I? That's my first question. And my second one is this is X, by the way. All right, take boards.
One thing I really like that Dr. Dawson is,